All right, let's jump right in. We're about to look at something pretty wild in engineering. A place where you make something stronger by, well, stretching it almost to its breaking point. And the craziest part? It's happening in something you see every single day, your car.
3,000.
So, what's that number? Well, that's roughly how many individual spot welds are holding your car together right now. Think about that. Thousands of tiny points of fusion, they're really the unsung heroes, turning all those separate sheets of steel into the solid protective frame you rely on. But here's the paradox, right? The very process that joins everything together, what if it's also creating a hidden weak link? I mean, that intense heat you need for a weld. It's essential, yeah? But it's also changing the steel in ways you just can't see, creating a vulnerability right where you need the most strength.
Okay, so to really get our heads around this hidden weakness, we've got to zoom way in. I mean, microscopically. Let's break down the anatomy of just one of these spot welds.
So what we're looking at here is a cross-section of a weld. Right in the middle, that's the fusion zone. That's where the steel literally melted together to create the bond. On the outside, you've got the original, untouched base material. But the key area for our story, it's that zone in between. It's called the heat-affected zone, or just HAZE for short. And this, right here, is where our problem starts. And this image, this hardness map, just lays it all out, doesn't it? See those blue and green areas? That's our culprit. That's a soft zone, a spot where the steel's strength has just plummeted. And it forms right in that heat-affected zone we just talked about. You can think of it like the fragile skin around a healing wound. It's an unavoidable side effect of all that heat. So, why does it get soft? Well, it all comes down to the steel's internal structure. On the left, that's the good stuff. The original, high-strength steel. It's got this really strong, organized crystal structure. But then, look to the right. Inside that soft zone, the heat has just created chaos. It's completely disrupted that nice, strong structure. And that's what makes the material lose its hardness. And this chart really puts some numbers to it. I mean, look at this. The original steel has a hardness of about 330. The weld itself, the nugget, is even harder, up at 430. But that soft zone, the part right next to it, it just tanks all the way down to 250. That's not a small drop. That is a major weak link sitting right at the edge of the connection. Okay, so we've found the weak spot. The question now is, what does that actually mean over the lifetime of a car? How does this vulnerability play out in the real world? Let's take a look at how engineers actually test for this. What you're looking at is something called a Wöhler curve. You can think of it like a stamina test for the weld. The higher up you go, the more stress you're applying. The further to the right, the longer it lasts. And for a standard, out-of-the-box weld, see that steep downward slope? It tells a clear story. The more stress you put on it, the faster it fails. It's the classic problem of metal fatigue. And this is what that graph looks like in reality. It's not just a line on a chart, it's a crack. And notice where it starts, right at the edge of the weld, exactly where we found that soft zone. From there, it just spreads until the whole joint gives way. This is the real-world consequence of that hidden weakness we identified. All right, so we've got the problem, we know the cause. But the solution? The solution that researchers came up with is just wonderfully counterintuitive. You'd think you'd need to add more material or change how you weld, right? Nope. It's something much, much simpler. And this is the big idea right here. What if you could make that weld stronger for its entire life, just by stretching it once? A single, controlled overload. Could that one action permanently change the weld and make it way more resistant to breaking down over time? And the process itself is just so elegant. It's basically 3 steps. Step 1, engineers take the finished weld and apply one single precise overload. Step 2, they release the load. And step 3, that's it. A protective stress is now permanently locked into the steel. That one cycle is all it takes. So what's actually happening here on a mechanical level? This chart shows it perfectly. As the load is applied and then released, you see how the line doesn't go back to zero? A little bit of that strain gets locked into the material, a compressive strain. It's like you're creating a permanent, microscopic clamp around the weld, a protective squeeze that's holding it together from the inside out.
Now that's a really clever idea, but the big question is, does it actually work? This is where the data comes in and just blows you away. Let's look at the proof.
So here we go.
The head-to-head comparison. Let's put them side by side. Weld stamina. The standard as-welded joint versus the one that got that single overload treatment.
And wow, the results are just stunning. That bottom line, that's the original weld. That top line, that's the weld after being stretched just once. This isn't just a small improvement, you guys. This is a massive, massive leap in durability. The treated welds can handle way more stress for way, way longer. How much longer? 50 times. Let that sink in. At certain stress levels, the treated weld lasts over 50 times longer. That one simple stretch increases its life by a factor of 50. That's not an improvement, that is a complete game changer.
Okay, so let's pull back and wrap this up. What does all this mean? Why is this so important? Well, for one, it's a simple, elegant fix for a huge engineering challenge. It means we can seriously improve the durability and the safety of our vehicles. It makes using these awesome, lightweight, high-strength steels much more reliable. But I think the coolest part is how it turns the material's own properties against its weakness. And the official name for this is compressive residual stress. That's the science behind it. It's that beneficial, locked-in squeeze we were talking about. It acts like a permanent clamp, literally holding the material together and fighting back against any cracks that try to form.
And that just leaves you wondering, right? If such a massive improvement in strength can come from something so simple, so counterintuitive, what other amazing fixes like this are just hiding in plain sight in the very materials that build our entire world?